Hello everyone, welcome back to the channel. I am Sanket Singh, and from this video we are going to start a very interesting series. A lot of people actually ask me about what is one of the most important topics to learn in data structures and algorithms. And the first topic that I always tell is time and space complexity analysis. Yes, time and space complexity analysis is one of the most important topic that you need to know in the classes of I would say data structures and algorithms. In any algorithmic interview, if you do not give the right complexity analysis for the code that you have written, then probably the higher call that you might have got will convert to a no higher call. Time and space complexity is very important, and a lot of people actually struggle to figure out the right complexity altogether for a given set of questions. And what we're going to do is we're going to start a 5-part series in which we are going to take a very deep dive into understanding time and space complexity analysis altogether. I am really excited for this. I hope you guys too. In this first part of this series, what we're going to do is we're going to start with the basics of time and space complexity analysis. We will see why do you need to do time and space complexity analysis, what are the different ways in which you can do this analysis and whatnot. That being said, without any further delay, let's just start. But before starting with the video, if you have not yet subscribed to the channel, do consider subscribing to the channel. We are going to put some really awesome content on this channel coming up ahead. So let's just start. So guys, before moving forward, there is a very important information that I would like to give you. So recently we wrapped our Elite 1.0 front-end development course, and now we have launched our Elite 2.0 advanced front-end development course. This is a bigger and a better front-end development course that you need. This course doesn't need any particular prerequisite, and we are going to take you from the very beginner level to the advanced level of front-end engineering. We have actually included projects like your own Replit clone, Wix website maker clone, right? Uber clone, and a lot of similar projects. You are going to make your own PubSub library based LLD driven projects, and we are going to make sure that you learn important front end design patterns as well. I'm going to list down all the projects and all the important design patterns here. This is the only course that you need if you are aiming for SD1 or SD2 or SD3 kind of roles, because we are going to take everything to the very advanced level in front end engineering. We are going to learn a lot of optimizations, and we are going to see technologies like Next.js, Redux, Zustand, TypeScript, React, and of course, the latest version of React. This particular course is going to make sure that you have ample amount of projects that you can add in your resume. We are going to make approximately 20 plus projects with different variety of complexities, engineering problems, and of course, there will be a lot of discussion around the core concepts of frontend. So what are you waiting for? Check out the course link in the description below, and you can use the coupon code mentioned in the description section to get maximum discount possible. See you guys in the cohort, and let's get back to the video. So today we are going to talk about a new topic, and this is one of the most important topic in computer science. If you want to become a software engineer, this is one of the most important topic. This topic is called as time and space complexity analysis. A lot of people also just term it as algorithm analysis. Right? Or algorithm complexity analysis. Algorithm complexity analysis. Right? So what is this topic all about? First of all, we need to understand the agenda for this topic, that why do you even want to learn this topic? Why this topic actually makes sense? Why is it important? Right? Just think about it. Just think about it. Let's say you want to use the Zomato's food ordering app, right? Let's say Zomato, Food Panda, right? Any food delivering app you are actually trying to use. And let's say you just opened the app, and there are a lot of restaurants. There are a lot of restaurants getting listed. Okay. But let's say you want to rearrange the restaurants, right? Or that you say that sort or filter the restaurant based on, let's say, rating. That those restaurants which are having higher rating should be present at the top of the screen. So it should be a decreasing order of rating. You want to rearrange it. Similar kind of a use case you can even get on any e-commerce app. Let's say you are using something like Flipkart or Amazon. and there are a lot of products getting displayed. There are a lot of products getting displayed on Amazon's website. Let's say you want to buy a new computer or something, and let's say here also you want to just filter all the products based on, let's say, a company, or you want to sort them based on the rating, right? Or you want to rearrange them based on their price. These kind of operations you want to do, right? Now just think about it. What kind of experience you will get if this process is very slow? For example, to rearrange all the restaurants or to rearrange all the products getting rendered on Amazon, let's say instead of a millisecond, it takes, let's say, 10 seconds. I know you might feel 10 seconds is not very much, but still 10 seconds is considerable. Do you think you are going to wait for 10 seconds for your Zomato's app to rearrange all of the data on the screen? 10 seconds, not even 5 seconds we are going to wait. We are not going to wait even for 5 seconds, right? Why? Because this is a very simple task, and we are going to expect that a scale an app of a scale of a Zomato or similar to scale of Amazon or Flipkart, they should do these algorithmic operations very easily. This is a very simple algorithm to rearrange a few things, right? So in how much time you are getting an algorithm executed makes sense. We are going to build products. We want to become a software engineer. We are not only just going to solve problems, but we are going to build products out of it. And a product is going to be dependent on how smooth your overall process is there in your application. And at a lot of places in your application, things are going to be algorithmic, right? Just think about it. If let's say you are going to put some expression in the calculator and calculator takes 1 minute to calculate all of that, it's going to be a very bad experience. People are not going to use my calculator, or people are not going to use Zomato, right? So having a good experience depends on how fast your algorithm gets executed, right? Overall in the app there are a lot of other things. For example, there is an internet involved. Let's say you want to download some images in your app, so definitely it will depend on kind of like the internet speed and everything. Those things are separate. But let's say something which is based on algorithm, something which is algorithmic, something which is logical based, and that thing is taking a lot of time, then that's is a very bad user experience. So efficiency of an algorithm in terms of time is very important. I can definitely state that efficiency of an algorithm in terms of time taken is important. That how much time the algorithm is taking, right? Second thing, now just think about it. If let's say you are running your Zomato's application and you want to rearrange all of these restaurants or food items based on their rating. And in order to execute this algorithm, your Zomato's application, let's say, start taking 512 MB of space, or let's say 1 GB of space extra, apart from what space has been allocated to your Zomato's application. Apart from that, it takes extra space, something like that, right? Then what will happen? It will add extra burden to my memory, right? It will add extra burden to my memory. Yes or no? Think about it. If for executing anything, let's say there is a camera application and your camera application is processing some photos on the device only, and it starts taking a lot of memory. Then also if let's say your phone is not very powerful, if it's let's say not having a 8 gig RAM, let's say it is only having 2 gig RAM, then the overall user experience will hamper, right? Because the phone will start freezing. The other applications which are running in the background might crash, or they might restart because this current application is taking most of the space. So whatever algorithm you are implementing, the efficiency of an algorithm in terms of space slash memory taken is also important. Can I say that? This thing is also important. This term is also important. And that is why now we all know how to write basic algorithms. It is very important for us to understand how exactly algorithms efficiency is measured with respect to how much time it is going to take and how much space it is going to take, because these are one of the most important metrics that exist out there, and we have to follow, we have to somehow make sure that we write efficient algorithms, we write algorithms that are fast, that take less space, and hence the overall product that we are going to build or the solution that we are going to build is as good as possible. So now let's just think about it. Let's just think about it. If I talk about the fact that when we used to buy computers, when we used to buy our brand new personal computer or laptop, what all things we used to be most concerned about? Let's just think about that. Or maybe even you buy a phone. Then the most concerning things are, what is the CPU involved in the computer, right? What kind of storage you are using, whether a SSD or a hard disk drive, how much and what version and what type of RAM you are having, right? Then apart from that, after that, we used to see if we have some good budget, then maybe is there a GPU, right? And a few more stuff like good display and everything. But good display and all, it is like secondary, right? Our first requirement for a good computer system should be some properties around this. And why these properties? We need these properties because the better the CPU and the better the RAM and higher the RAM, better will be the processing that we are going to do in our computer, and better will be the process management, because all of the processes are going to be loaded inside RAM, right? And every processing is going to be done inside CPU. So we want a good CPU and we want a good RAM. Similarly, if you have a graphic intensive task, then GPU is going to enhance the overall efficiency of the graphic intensive algorithm. SSD and HDD we use for good storage, but that's a secondary storage where we have to store files. But for storage, we need good size of memory, right? Like nowadays, people opt for like 8 gigs of RAM, 16 gigs of RAM, because nowadays processors are getting heavy. So they also need good amount of RAM to make sure everything is smooth. But all of these things are there to make your experience smooth, right? But don't you think these are hardware capabilities? We are software engineers, right? Just think about it. If let's say we have two users, let's say for the same algorithm, we have two users, user 1 and user 2. User 1 is having a very fast Apple M1 processor, right? It is extremely fast, comes with the latest build up technology, right? See, up to 2.x times faster than their own previous processors and everything. And another user is there who is having an old Intel Core 2 Duo processor. It's not bad, but it's old. That means it cannot just directly compete with the processing capabilities of the latest processors like i9 or M1 Pro or M1, these kind of processors. So let's say we have two users that are using our applications. And in our application, we are writing some algorithm. Now, don't you think the user who is having a better overall configuration of the system will eventually get a better experience, and the user which is having a lower configuration system, let's say less RAM, old processor, they're going to get not that good experience, right? So as a software engineer, we cannot just make an algorithm such that we will say that, okay, if the user is having a good system, then our algorithm will work very good. If the user is having a bad system, then our algorithm should be like, just get a new system. We can't just ask our users to do that, right? We can't just ask our users to upgrade every now and then, because we are not writing good algorithms. If we will write efficient algorithms, then technically it will work almost in the similar fashion in both of the system. It will not be a drastic user experience difference. But if you will write bad algorithms, then maybe it might work well on this, but it will definitely not work well on this, right? This is something there, right? So as a software engineer, it is our duty to make sure that the algorithms that we are going to make is efficient in every possible situation. To whatever extent it can be, it should be efficient to every possible situation. Right? Now just think about it. Let's say, let's say I write an algorithm. I write an algorithm and I execute that algorithm in the M1 processor system, which is, let's say, having a 16 GB RAM, for example. And let's say in order to complete this process, in order to complete this algorithm, let's say it takes 100 milliseconds here. Good enough? And let's say the same algorithm, if I am running on this Intel Core system, right? Let's say it is taking 450 milliseconds. Not that bad, but still not as fast as this, right? Now just think about it. It is evident, right? It is evident that if you run the same algorithm on two systems, then definitely M1 system is going to execute everything faster. It is having the latest technology, best built up system, better silicon technologies, better processors are involved. So it's going to run something quite fast. And Core to Duo is definitely, or something older than Core to Duo or something like i3 is going to struggle a bit. So if we are judging the algorithm, let's say if we want to see whether the algorithm is working well or not, do you think, do you think this criteria of how much time the algorithm is taking in order to get executed, should this be a metric of measurement? What do you think? Should this be a metric of measurement or not? Because if I want to judge my algorithm, I'll run it on a faster machine. It will work very well. So it's not going to be a good way to judge the algorithm, right? Because the algorithm will run fast on a faster machine and it will run slow on a slower machine. It doesn't tell us about the nature of the algorithm. So my point here is, when we are judging algorithms, that which algorithm is better, we can't rely something which is dependent on hardware, right? Because if the hardware is better, it is definitely going to execute things in a better way, in a faster way. If the hardware is not that good, it is going to somehow struggle. But this thing doesn't tell us anything about how good our algorithm is. So the judgment of the algorithm should be independent of the hardware that we are testing on. This is my first claim. This is my first claim that I want to make. Now let me tell you one more interesting thing, based on which I will justify one more thing around this notion that your algorithm should be independent, or your measurement of how good the algorithm is working should be independent of the hardware that you're using. Okay. So let's say this is a simple piece of loop. In any language, you can write this loop: C++, Java, Python, JavaScript. This is a JavaScript file. But in any language, just write this loop. Okay. A simple loop, or something else if you want to write. So now let me just run this code. Let me just run this piece of loop in front of you. Now you can see I have not printed anything. Let me just print it very quickly. Console.log end. Okay. Now if I run this code, you can see it prints end and it printed in 0.05 seconds. Looks good. Okay. I'm not making any change to the code. I'm literally not making any change to the code. Let me run it again. Do you see the time taken to execute the same piece of code that I didn't even change is now different? Let me do it once again. This time, the time is same as the second time. Okay, let's do it again. This time it is again different. See, every time almost that we run the code, the time taken to execute the code, which is just a simple for loop, is different. Why is that? What is going on here? And it's not something that is just going to be with JavaScript. Any language that you are going to use is going to behave in the same way. Because there is a very interesting fact that is hidden behind how computer handles your process execution that we are going to talk about. Now let's try to understand what actually goes on. So in modern computers, you must have heard about this term called as multitasking. Right? It's a very common term and a lot of people technically use it. But technically, there is nothing like multitasking that happens in the computer. If I talk with respect to just a single core, right, that in CPUs there are multiple cores. For example, octa core system, hexa core system, quad core system, right? There are multiple cores. If I just talk about a single core of the CPU, there is nothing like multitasking that actually goes behind the scenes. There is nothing like multitasking. Like, if let's say if you assume that my current computer is only having one single core, then there is no multitasking that is going on. Then what happens actually? What happens? So technically, when your CPU has to execute some tasks, when your CPU has to execute some tasks, that task can be some internal task or some internal process. That task can be dependent on some input output from the user also, right? So what actually CPU does is, CPU maintains something like a queue. What is a queue? If you don't know about a queue, queue is just like you stand in a line, right? You stand in a queue of for buying a ticket, for buying a product or something. It's something like that. So there is something like a queue that is maintained. Something like a queue that is maintained, right? What CPU actually does is, let's say there are multiple process. Let's say there are three process. Process P1, process P2, process P3. So it's not like process P1 is getting executed parallel to process P2 and parallel to process P3. No. In a single core of a CPU, this thing doesn't exist. If there are multiple cores, then in one core there can be a process, and parallel to that in the other core there can be other process. But if you just talk about a single core system, nothing like parallel execution actually works. What happens is, let's say the CPU has to execute multiple processes. For example, it has to execute Chrome also. Maybe I'm trying to execute some JavaScript code. Let's say there is some MS Paint opened or some text editor opened, right? There are multiple processes. What CPU does is, it picks a process. It picks a process, right? Let's say it will pick process P3. It will pick process P3, right? And what it will do is, it will just execute some part of process P3. It will just execute some part of process P3, right? Let's say there were like 100 instructions. I'm just giving you some random number. Let's say there were total 1000 instructions that were expected to be done for executing the process P3. Let's say your computer will only do around 500, or let's say even less than that. Let's say 300, right? Let's say your CPU will just execute 300 instructions at one point of time. And then what it will do is, it is going to send the process P3 in a waiting state. So see, you have some partially executed swapped out process. Swap out. What is swap out? Swap out means CPU has executed some instructions and it will just throw it out of the current execution flow. And this process P3 is now going to wait here. This is kind of like a waiting area. This is kind of like a waiting area, right? P3 is going to wait here. And then CPU can pick some other task. Let's say CPU picks P2. CPU picks P2. Inside P2, let's say there were 5000 instructions that were expected to be executed. CPU just executed, let's say, 800 of them. It's not like it will always execute same number of instruction for everyone. No. So let's say this time it executed 800 instructions for P2, and then it is going to send P2 also in the waiting area, right? Then let's say it picks P1. Let's say it picks P1, does the same thing for P1, right? And then when everything is now in the waiting area, then maybe it will pick something from the waiting area. Now let's say it will again pick, see, from this waiting area, it will try to swap in again. Swap in means it's now going to pick something inside my queue. So let's say first it will pick again P3, but then P1 and then P2. So it will again come back to this queue kind of a thing. Then again, let's say it picked, for example, P2 this time. Why? Right? Let's say it again executed something like P2 this time. Then let's say it executed 1000 more instructions for P2. Then it will again send P2 in the waiting area, which will later come in the queue. and let's say this time it starts executing P3. For P3, let's say it executed all of the remaining instruction and P3 is done, right? These things happen. And then let's say in between this, all of this execution, you as a user gave some input. Let's say you put a keystroke, like for example, some mouse click or some keystroke, some kind of input you gave in some way. So that input is also going to be processed, like that instruction is also going to go inside the ready queue, which will be later picked by CPU. If there are multiple instructions, so it might execute some of them and then send them back in the waiting area. And why CPU does this? Because a single core cannot execute everything parallelly. Just think about it. If you are sitting at your home, you are doing the dinner, then if somebody asks you that during your dinner you have to read a book and you have to watch a movie and do the dinner also at same instance of time, like at the, let's say at 10:48 p.m, exactly this 48th minute, and let's go even precise, let's say at 10:48 p.m, and let's say 35th second, at the current 35th second, do you think at the same point of time you are eating also, you are reading the book also, and you are watching the TV also? You as a human, can you do all the three things parallelly at one instance of time? Let's say at one some millisecond or some second. Are you technically doing everything parallelly? No, right? Same thing with CPUs. That this single core is something like, it's a way to process some data, to process some instruction. It cannot process multiple things. It is not having the capability to do something parallelly. The parallel capability actually comes when there are multiple cores, or there is a concept called as thread, that something like that gets executed, right? Or there are some other ways also in which people generally handle this, but at one point of time, a single core can only execute one instruction from one process. But the main thing is, modern CPUs are so fast, like even a dual core or a i3 is so fast that in 1 second, a CPU can execute approximately 10 raised to the power 8 instructions, sometimes even more than that. In 1 second, they can execute 10 raised to the power 8 instructions. Now just think about it. If let's say they get 3 process, and total these 3 process have got just 10,000 instructions, this is nothing compared to the capability of the CPU, right? CPU can execute 10 raised to the power 8 in 1 second. You are barely giving it what, 10,000 or 1,000 or something. So it's nothing for the computer. So what actually computer does is, in 1 second, it has the capability to execute 10 raised to the power 8 instructions. So what it does is, it executes some instructions from one process, very quickly put it to the waiting area, picks another process, executes something very quickly, puts it there. And this process happens so fast that we feel like it's actually multitasking, right? That is why and I told you, right, when it is picking a process, it's not like it is going to execute same number of instructions every time. See, P3 got instructions executed 300, let's say P2 got 800, because how many instructions it is going to execute depends on multiple things. For example, let's say P2 is a high priority task. Now in CPU or your computer also, there are some high priority tasks. For example, if the CPU will not execute this task very quickly, then the whole system can crash. Let's say there is a task that maintains the overall, I would say, operating system somehow. And if you will not very constantly execute that task, your CPU can crash, your OS can crash. Then it's a very high priority task, right? It's a high priority task. That means it needs to execute faster. It needs to get the chance first. Let's say everything is now in the waiting area. Which process to pick? There are multiple ways in which you can pick a process. Let's say which the process that went to the waiting area first is the most waiting process. You should pick that. But maybe there is a high priority process. Then you will pick that high priority process first, right? Because even if the other process are waiting, the CPU is not going to crash. But if this process is going to wait for a long time, CPU can crash. So there can be processes that are of higher priority. Then the other processes are going to wait, right? That's why when your process is going to be picked up, when the instructions are going to be executed. How many instructions are going to be executed when you get a chance here? You can never determine. That is why when I run when I run a for loop, or when I run a piece of code, when I run a code, you know that, right? Your program gets converted to a process. That means it gets loaded in the RAM and its instructions start getting executed in the CPU. Now, when your program or when your process is going to get a chance to get executed in this whole cycle, how many number of times, how many instructions in one cycle it is able to execute, a lot of factors are there to determine how much time your process is going to take. See, earlier it was fast, so most probably it got the chance earlier. This time it was a bit slow, so with respect to the other processes, it got the chance a bit slower, right? Sorry, this was faster. 246, 046 was faster. 0.232 was slower, right? So in the previous turn, it got the chance very late. But it is 0.232 seconds. We don't even feel it. We don't even feel it, right? Even if it takes 2 seconds, we won't be most probably feeling it, right? It's so fast. It takes 0.039 seconds, but it is still so fast, right? So we as humans, we feel that the computer is actually doing multitasking because 10 raised to the power 8 instructions is huge. This is a huge number that a computer can handle. And mostly, even if you get an M1 system, or maybe you get a core to dual system, this number is going to be approximately same. This number is approximately going to be same for a single core. Always I say with respect to a single core. When there are multiple cores involved, and let's say there is a very huge generation gap, like if you go for some microprocessors which are like 8080, 8085, those very old microprocessors, and then you start comparing them with M1 Pro or M1, then there will be a drastic change. There can be some drastic change. Maybe they are only able to handle 10 is per 6 instruction because they're extremely old, like generations old. But if you just compare i5 and M1, then this number is going to be approximately same, right? In 1 second, your computer can execute these many instructions, right? That is why we feel like everything is going quite parallelly, but actually it's not with respect to a single core. Yes, if there are multiple cores, then in every core, this same thing happens parallelly. So in every core, there is a ready queue. Every core is technically a CPU process, CPU that can process your instructions. So if there are multiple cores, then there is actual parallel processing going on. But if there is a single core, then technically there is no parallel multitasking that is going on. This is why we cannot rely on analyzing an algorithm based on machines. Because even if you have a fast machine and you analyze both the algorithms on the same machine, there can be a case that your algorithm 2 was better than algorithm 1, but it got the chance of execution in CPU late, right? And every time it used to get a chance, only very less instructions were getting executed because maybe there was some higher priority task that came up. That is why analyzing your algorithms based on a particular machine is the worst way that you can go for. Because if I've asked you to analyze it like this, what you will do? You will write two algorithms and you will just measure the time of execution. The best that you can do is take 10 or 100 readings and take an average out of it. But still it doesn't make sense because it can be extremely late also, right? This kind of analysis is called as experimental analysis. What is experimental analysis? In experimental analysis, we actually try to see how much time the algorithm is taking to execute, and then only we execute it, right? And based on that, we actually make the decision on which algorithm to pick, which algorithm not to pick. But this experimental analysis where you actually see the time taken, that's not the best way to go for.